Okay, so I'm going to talk to you today about reconstruction using parallel architectures. So this is sort of a shift in topic. So in a liquid argon neutrino experiment, the neutrino interacts and produces charged particles, which ionize the argon. And these ionization electrons drift in an applied electric field and are collected on a set of wires. And so what the detector reads out in the end are basically charge as a function of time on each of many, many thousands of wires. And so this means that the reconstruction time will scale with the size of the detector and the number of wires, which is expected to increase by orders of magnitude over the next generation of experiments. So we're using parallelism and modern computing architecture to improve the reconstruction time for an event and to prepare for these next generation experiments. So the algorithm that I'll focus on here is the Gauss hit finder. This algorithm is what takes these pulses that are produced on the wires and identifies and extracts parameters associated with these pulses. So here, this is so the position, the amplitude, and the width. And this algorithm is well suited for parallel implementation because each of these wires are independent, so they can be processed independently. Furthermore, there's good potential for impact because this algorithm can be up to 30% of the overall reconstruction time, depending on the experiment. So we've tested these developments using a standalone piece of code. We implemented the Levenberg-Marquardt algorithm to do the fitting, which is a change from using root-min-wee previously. We vectorize both using compiler vectorization with AVX512 and then also using explicit pragma calls on the most time-consuming loops in the fitting as determined by profiling. And we multi-thread using nested OpenMP parallel for events over events, which are independent, and regions of interest on the wires, which are also independent, and use dynamic thread schedule. So these are the results for the standalone code compiled with AVX512 and ICC. We find that with vectorization, we can get 2 times faster on both KNL and Skylake. So here at 1 is with no vectorization, and then over here is almost at 2 times faster with vectorization. For multi-threading, we see near ideal scaling at low thread counts and up to 30 times faster on a Skylake. And for a KNL, this is 100 times faster. So this code has been integrated back into LARSoft for general use by LAR TPC experiments. And single threaded within LARSoft, it's 12 times faster for the Microboon experiment and 7 times faster for the Icarus experiment. And both Icarus and Protodune use this version of the hit finder. So in order to take advantage of this and other developments like this, we are developing a workflow to run part of the next Icarus production on the Theta HPC at Argon National Lab. And here our strategy is to do a local build of LARSoft at Theta with SPAC. And this will allow us to take advantage of the parallelism not available in a typical grid production environment. And also to customize the compiler options for specific pieces of code, such as the combination of AVX512 and ICC with the Gauss hit finder. We will use HDF5 and Hepnos to organize the data and DIY to distribute across the nodes. And so at this point, we have the first SPAC LARSoft Icarus code build on a non-Fermilab computer complete, and work is ongoing to compile on Theta. So in conclusion, techniques like vectorization and multi-threading can be used to optimize and improve the performance of liquid argon neutrino detector reconstruction algorithms. We have one such example that's vectorized and multi-threaded and can be up to 200 times faster in a standalone version, and before multi-threading, up to 10 times faster in LARSoft. And work is ongoing to take advantage of this in a production environment for a liquid argon neutrino experiment that's collecting data. Thank you.
Great, thanks very much, Valentine. And so we have a few minutes for questions.
Sophie, I can't raise my hand because I'm a host. So Sophie, thanks very much. That was a really nice talk. I was just wondering if you could comment on, how much of the code you had to hand vectorize, and if what's your sort of feeling ongoing, because generally those were great things to demonstrate performance, but they did not produce maintainable code.
Yeah, so so our vectorization happened just within the hand vectorization was just within the Levenberg-Marquardt algorithm implementation itself. So sort of within the fitting algorithm. And we compared also to some libraries and found that our hand version was better, but I think that keeping it sort of within the fitting part of the code as opposed to within the experiment part of the code should hopefully help in order to, so basically you can switch out the fitting algorithm that fits the Gaussian peaks if a better one comes along.
Okay, thanks. Yeah. I think SPAC, just another comment as well, is I think SPAC is quite good at, maybe compiling for particular architectures and switching that in and out depending on what nodes you're actually running on. So yeah, it's a bit of a problem, but on the other hand, if the speed gains make it worthwhile, it's maybe worth the effort.
Yeah.
I see this one from Sun Young.
Sorry. The ABX 512, in principle, you could get up to factor 8 for vectorization. Your result shows a factor 2. Do you understand where this speed up lost?
Yeah, I think that it comes from a challenge in vectorizing basically a minimization algorithm, because the compiler can't know in advance how many iterations it will take to minimize a particular case. And so I think that's one of the challenges in terms of the vectorization, is to really get that right. And yeah.
Okay, I see Josh has his hand up. Is this a response or a new question?
Well, it's a sort of related question.
Go ahead.
Yeah. So linking to the theme of the previous talk, I mean, do you use analytic gradients in the minimization algorithm?
We use, I mean, I guess there is what we use just basically, sorry, I maybe don't know the answer to this.
No, because I guess the point, so in Minuit, certainly the gradients are always computed by finite differences. I don't know how you do it in your minimizer, but typically if you have the gradients computed either analytically or by autodiff, then usually it's more stable and you can get convergence in fewer iterations.
Excuse me. Hello?
Yeah, please.
Yeah, this is Mike Wang. Yes, we do. We use analytic gradients.
Okay, thanks.
Thanks, Mike.
Okay, I think we have to wrap up the discussion there. So thanks again, Sophie, and for